Our goal is to examine a couple of examples. In the first example on the screen, we talk about the Best Health Corporation, which makes and distributes health products. The company's research department is experimenting with two new herb-based weight loss enhancing products. Now, to gauge their effectiveness, suppose the researchers at the company conducted a test using 300 human subjects over a 6-week period. All the people in the study were between 30 and 40 pounds overweight. Now, one third of the subjects were randomly selected to receive a placebo. In this case, it's a pill containing only vitamin C. The other one third of the subjects were randomly sampled and given product 1, and the remaining 100 people received product 2. The subjects did not know which pill they had been assigned. Each person was asked to take the pill regularly for 6 weeks and otherwise observe his or her normal routine. At the end of the 6 weeks, the subject's weight loss was recorded. The company was hoping to find statistical evidence that at least one of the products is an effective weight loss aid. Now, positive values indicate that the subject lost weight, whereas negative values indicate that the subject gained weight during the 6-week period. As often happens in studies involving human subjects, people drop out. Thus, at the end of the 8 weeks, only 89 placebo subjects, 91 product 1 subjects, and 83 product 2 subjects with valid data remained. Consequently, this experiment resulted in an unbalanced design. You see, this is meant to remind us, first of all, that if we have an unbalanced design or an unequal number of subjects being exposed to different treatments or levels of a particular factor, then we have an unbalanced design. And what kind of effect can that have on our test or the validity or the results of our test? Well, if for some reason you're unable to find enough data to use a balanced design and you end up with an unbalanced design, the rule of thumb is that as long as the ratio of the largest sample to that of the smallest sample does not exceed 1.5, then the analysis of variance procedures still come out with results that are still very, very valid. In other words, the output is robust with respect to the assumption that the populations are normally distributed. So, in this context, then, the appropriate null hypothesis is to look at the three groups: the placebo group, the product 1 group, and the product 2 group. And we would like to state the null hypothesis where we say that the average response value for the placebo group is the same as the average response group for those who received product 1 and the average response value for those who received product 2. Whereas the alternative will say that at least one of these means differs from the others. Okay, so with that said, our interest then is to carry on our hypothesis test. And for this ANOVA, of course, we usually would like to collect our data values and do some model check. All right. To do that, let's look at the data set. I'm going to close out of this. And in this case, I have the data set here. We have the subjects, and we have those who received the placebo group, who received the placebo, hence those who ended up in the placebo group. And this is talking about weights. In this case, if you have a positive value, it indicates that the subject lost weight, whereas negative values indicate that the subject gained weight during the 6-week study period, and the subject's weight loss was what was recorded. So we want to know if the weight loss is due to what products they received. Is it the placebo, the product 1 or the product 2? Is there any difference in the average weight loss across the three groups? So to do that, we would like to look at if the populations are normally distributed. To do that, you can go to graph and plot a histogram of each of the three uh, of the values collected on each of the individuals in the three groups. So you have placebo, and we have product 1 and product 2. And let's see. And I would usually like to see where the mean is for each of the groups. And I also like this to have 1, 2, 3, 3 rows. So I want 3 rows per page since I have 3 groups and compute. And I have the histogram here, which I have taken into our workbook. And I can see that this group is approximately symmetric, normally distributed. This is also approximately symmetric, and this is also approximately symmetric. So the assumption of normality of distribution, if it is reflected by the samples taken from each of those populations, is well documented. Then, what about the assumption that the population variances are equal using Levene's test? Well, what we need to do is to go back again into StatCrunch. Let me close out of this. And I'm going to go to Stats, go to ANOVA, one-way ANOVA. And in this case, I'm interested in placebo product and product 2. And in this case, I have selected what columns in the different what groups here. And my interest is to also compute my Tukey LSD, which we'll talk about in just a little bit. And what? The test of homogeneity of variance using the Levene's test. And I would like to compute. And what I need in particular here to check for the assumption that the population variances are equal is the Levene's test, which has a p-value of 0.1888. This is greater than 0.05. When the p-value is greater than 0.05, we fail to reject the null hypothesis, which means we conclude that the variances of the groups are equal. So that meets that requirement. And for the sampled observations being independent, it suffices that if we randomly sample people, then this requirement is met. And lastly, the data's measurement is interval or ratio, indicating that the data values are numerical. Of course, these are numerical values. Okay, and with that said, we're ready to jump into the mechanics. So we have the ANOVA table, and in particular, we need the p-value. So pulling the p-value here, so we have the p-value, which will be used to draw conclusion. This is significantly lesser than 0.01, which itself is already less than 0.05. When p-value is lesser than 0.05, what do? We reject the null hypothesis. Let's go back to what that means. If we reject the null hypothesis, that means we are concluding in favor of the alternative, that at least one of the means differs from the others. If one of the means differs from the others, it means that we have sufficient evidence in the sample data to conclude that at least one mean differs from the others. That is, the difference in the means may be attributed to the effects of the products as an effective weight loss aid. Now, we said that at least one of the means differs from the others. That leaves us with a question. Which of the means is different from the others? Is it the first one different from the other two, or the second one different from the other two? Which is it? So there is an open-ended question here. And to answer that question, we conduct what is known as a post-test or a post-op procedure. using Tukey's honestly significant what difference, shorthanded as Tukey's HSD. You see, Tukey, a statistician, could have called it Tukey's no-nonsense difference. Why? Because that's the real spirit here. Because after ANOVA shows that at least one group differs, HSD tells you which groups are truly different without lying to yourself through inflated false positives. It's the 1950s statistician ways of saying that we're not going to pretend that a tiny, flimsy difference are real. We're only interested in differences that are statistically significant. So to carry out this post hoc test, we already have the results here in StatCrunch. And what did we do to enable us get these results right here? Let's go back. Let's go to edit. We clicked on this checkbox. And if our alpha level is 0.05, the level of confidence then is the remaining 95%. So going back, we have what the results of the Tukey's HSD at the 95% level. What do these numbers mean? Let's go back to our table. What it means in particular is if we have a placebo group subtracted from product 1. So I'm going to write product 1 here. So I'm looking at the effect of product 1 compared to the baseline of the placebo. The effect is in the range of 2.4051626 to 6.0014555. These are both positive numbers. So what does that mean? It means that with the baseline as a baseline value, the values of weight loss due to placebo taking, if that is the baseline, and you look at how far the effect of taking product 1 is from those who took just the placebo, it only the range of the 95% confidence interval for that effect is from this value to this value. Since these are positive, this is a good time to go back to the context of the problem. It says that positive values indicate that the subject lost weight. So it means that taking product 1 as compared to those who took up the placebo help them to lose weight of between 2.40 pounds to about 6 pounds. Similarly, for the second part of our output here, I am again looking at placebo, the baseline, subtracted from product 2. And so I'm going to write product 2 here. And the effect that product 2 has compared with what? Placebo, the difference it makes, hence the minus, is between 2.49 to 6.17. So what do you think? Again, these are positive values. It means that the product 2 is performing significantly better than what? Than the placebo group in terms of weight loss. Then lastly, we want to look at the last possible pair. What about if we compared product 1, so product 1 compared to product 2. So I'm going to write product 2 here. Product 2. What do you notice? This goes from a lower value of negative to an upper value of what? Positive. So there were times when it was what? Negative, which means weight gain, and positive, which means weight loss. Take note that the interval from negative to positive contains 0. In other words, it is possible that the difference in the effects of product 1 compared to product 2 could be nothing. In other words, the difference between them is not really significant. And that is what Tukey's HSD is telling us, that the difference between the effect of product 1 and product 2 is not really significant. So what are implications of this? So for weight loss, product 1 or product 2 are both more effective than what? Than taking placebo. No treatment at all. That is what this 2 indicates. So you're welcome to take any. And also for weight loss, product 1 is almost as effective as product 2. That is what the last statement here tells us as far as what informed decision making is concerned. And that is where we conclude that question.